Welcome back, everyone. In previous lectures in this course, we have seen how to obtain the response of a single degree of freedom system subject to either free vibration or harmonic excitation, and we did that for damped and undamped system. But in reality, there are several other type of loading which may not be described using harmonic loading. And the example could be step loading, pulse loading, and other type of forces. So what we are going to start today is basically how to obtain response of a single degree of freedom system subject to arbitrary excitation. Okay, so let us get started.
Today we are going to start a new chapter, okay, which is basically the non-periodic excitation to single degree of freedom system. Okay, so right now we would only be focusing on single degree of freedom system. Now, if you recall from previous chapters, till now let us see what we have done. We set up the equation of motion for a single degree of freedom system, which we said the equation of motion for a linear system, it was something like this, okay, and this is equal to p of t, okay, and depending upon p of t, which is referred to as the excitation or the forcing function, we divided our study in free vibration and forced vibration. And in free vibration we first study undamped free vibration and then damped free vibration. Okay, now in the forced vibration we studied the harmonic excitation or the periodic excitation. Okay, so till now we have finished up to this part here. Now harmonic and periodic excitations are fine, but you will encounter many loads in a real life scenario which might not be either harmonic or periodic. Okay, so for those type of system it becomes imperative that we study these type of system. Okay, so response to subject to non-periodic excitation. Okay, and then later of course we'll study this, but today's chapter is focused on non-periodic excitation, okay, which is another common set of loading that are encountered in real life, and for which the approach to find out the analytical solution is little bit different than what we have studied so far for harmonic excitation. Okay, so again for this case our problem statement is, okay, problem statement is basically mu dot plus cu dot plus ku is equal to pt. Okay, and the initial conditions, okay, are given to us. Let us first take this as zero initial conditions. Okay, so this is our problem statement, and here the pt, the forcing function, is neither harmonic neither pure periodic. Okay, it's some arbitrary variation. Okay, so if you consider, let me just say any arbitrary variation of pt with respect to time. Let me just draw it like this. Okay, and then I need to find out the solution or the response of this single degree of freedom system subject to this. Okay, so let us see how do we do that. Okay, now for this type of functions pt, what actually we do in order to find out the response, we divide this function in very small intervals. Okay, so throughout the loading we divided in very small interval. Okay, and then at any time t, let us say this is at any time t, we try to find out the response ut subject to all these small durations loading, okay, up to the time t. Okay, so what do we do? Let us say I want to find out the response at any time ut. Okay, so I have the excitation function and I divide it in small intervals like this, okay, the response at time t ut, okay, would have contribution from each of these, okay, so let us say this and this, each of this small duration loading up to this point, okay. All right, so this is the strategy that we are going to employ, okay, and let us see how that works out. But before we get into that, we are going to introduce a new concept, okay, which is called impulse, okay, and we are going to talk about unit impulse, okay, response to unit impulse, okay, and I'll show you why do we do that. Okay, now an impulse, basically it is defined as a force, okay, so impulse is a very large force, okay, that acts for a very small duration, okay, that acts for a very small duration, okay, such that the area under, okay, the area under the force and the duration is still some finite value, okay, so basically the force that acts for a very small time and very large magnitude is characterized as impulse, such that it still has finite area under the force time diagram, okay. So let us say, let me draw an impulse like that. So what I'm going to do here, I'm going to write pt here, okay, and this is my time axis t. So I'm going to consider a force which is at time tau, okay, at any time tau, okay, and basically this duration here, okay, let me call it epsilon, okay, and this magnitude, basically this force is actually, I will call it 1 by epsilon. So what happens as epsilon goes to 0, okay, the p tau is actually goes to infinity, okay. However, even in that case, my p tau times d tau over the duration, okay, over the duration tau to tau plus epsilon would still be equal to 1, okay, and that I can see it from here. If I multiply basically 1 by epsilon with epsilon, I still get a unit area, okay. So this is one way to define a unit impulse, okay. So we said that the time integral is still a finite value even though the force goes to a very large value for a very small duration of time, okay. So this is the definition of impulse, okay. Now mathematically this kind of functions can be represented using something called delta, okay, Dirac delta function, okay. So let me just write it. It's called Dirac delta function, okay. And if you have come across this function previously, this basically says that delta x is equal to 1 for the when its argument of this function is actually equal to 0, okay, and it is 0 everywhere else, okay, it is 0 at all other places for x not equal to 0, okay. Now if I have to do this for this function, what I do, I represent this Dirac delta as this t minus tau, okay, so that this function is actually equal to 1 when t equal to tau, okay. So when t equal to tau, this argument again becomes 0, okay, same thing that we did here, okay, and this is 0 for t not equal to tau, okay. So this is mathematically how we represent the unit impulse, okay. Now according to the Newton's second law of motion, okay, if we have a force p, right? If we have a force P that acts on a body, okay, the rate of change of momentum of that body is basically equal to the applied force. Okay, so basically let me utilize the Newton's second law. Okay, the Newton's second law says that d by dt of momentum, and as you know, momentum is defined as mass times velocity, that should be equal to the applied force. Okay, and if mass is constant, I can write this as m dut, that should be equal to p. Okay, now we can go ahead and integrate both sides of equation so that we can get it as p. Okay, we can write this as p of dt integrated over time t1 to t2. Okay, let us say it goes from state 1 to state 2, then I can write this as m du times, okay, state 1 to state 2, and let us say that it went from velocity v1 to, okay, v2, or let us say it went from u1 dot to u2 dot. Okay, so that I can write this as m, okay, u2 dot minus u1 dot, okay, which is nothing but m delta u dot. Okay, so basically this term here that you see, this is the time integral of force, right? What we define as impulse. Okay, and as you can see from this expression, impulse is basically the change in the momentum. Okay, so if you apply an impulse of any body, that is basically it is equal to change in the momentum of that body. Okay, so let us say if you consider a single degree of freedom system that we have been dealing till now, again the same representation. Okay, we have a single degree of freedom system here. Okay, and I apply an impulse on it. Okay, so what's going to happen? Okay, if somehow I can calculate the magnitude of impulse, okay, that would lead to the change in momentum. Okay, and let us say this is a unit impulse, so that, okay, this is a unit impulse, so that I have let me just go back to that. The impulse is basically applied at time t equal to tau. Okay, so I will draw that figure again here. Okay, this is at any time tau. Okay, the force pt. Okay, so the impulse is at that time tau. This is a unit impulse, which basically means that my p tau, which we have derived, p tau times d tau is equal to 1 over the time duration. Okay, so when we have this system here, the spring mass damper system, and we apply a unit impulse at time t equal to tau, what will happen? It would lead to change in momentum. Okay, so let us say this unit impulse, okay, p tau times t tau, which is equal to 1, and if initially I'm assuming that the system was at rest, okay, after the time t, the velocity at time tau would be equal to, okay, m times u of tau. Okay, I'm assuming that there was no initial velocity. Okay, so that tells me that u of tau is actually equal to 1 divided by m. Okay, so if we apply an impulse to a system, it leads to change in momentum, which further gives some initial velocity to the system. However, it does not lead to any initial deformation. Okay, because the spring, as we discussed, impulse is applied for a very short duration, so the spring does not get time to actually react to that high magnitude small duration force. So what happens? Okay, so let me, this is velocity actually, don't mistake that. So initial displacement is still equal to 0. Okay, so with these conditions, Okay, what we want to do, we want to find out the response of this system. Okay, the response of this spring mass damper system with these initial conditions, and that would be the response to a unit impulse at any time equal to tau. Okay, so let us see what do we get. If you remember, okay, your expression for response to an undamped system, remember it is now like a situation in which the initial conditions have been given to you and you have to find out what is the further motion. So it works like when you apply an impulse, it provides initial condition and then it is like a free vibration. So after this, these initial conditions are applied, it would undergo basically free vibration. Okay, and if you remember the equation of motion for free vibration for an undamped system, let us first do undamped system, we'll again do the damped system. It was u of 0, okay, cos omega nt plus u dot of 0, okay, times sine omega nt, and there was this omega n term here. Okay, there is one small difference though. Here it was due to initial condition at time t equal to 0. However, for us, the initial condition is at time t equal to tau. Okay, so for our case, basically, the expression will become u of tau, okay, cos, remember our motion is starting at t equal to tau, okay, and there is no impulse or there is no any force before t equal to tau. Okay, so I'm going to shift my axis so that it becomes omega t minus tau plus u dot 0 omega n sine omega n t minus tau, because our impulse is applied for at t equal to tau, and this solution is only valid for time that are greater than tau, because if time is smaller than tau, the response is actually equal to 0. Now we already know that this is equal to 0, so we are only left with this term here. Okay, one correction, this should be here u dot of tau. Okay, so we'll substitute the value of u dot of tau, which is 1 by m omega n, and this is sine omega n t minus tau. Okay, and this function can also be written as a function of h of t minus tau. Okay, so this is for undamped system. Similarly, you can write the equation for free vibration of a damped system, and similarly get the expression as u of tau is equal to m omega n e to the power minus zeta omega n t minus tau, okay, sine omega d, sorry, it should be here omega d here, okay, t minus tau. Again, this we can write it as another function h t minus tau. This is for damped system. Okay, this is for damped system. So basically these h t minus tau are unit impulse response function. Okay, these are basically response of a single degree of freedom system due to unit impulse. So these are called unit impulse response functions. Okay, all right, so we have obtained basically the response due to unit impulse, and remember this is a response at any time t due to impulse at time t equal to tau. Okay, so let me write that again. Okay, response at time t due to unit impulse at time t equal to tau. Okay, now once we have that figured out, okay, we know that response due to unit impulse. Okay, now we can delve into finding out the total response, okay, subject to the arbitrary excitation P of t, which is varying arbitrary with time. Okay, so once you know the h of t minus tau, which is the unit impulse response function, remember this is the response due to unit impulse. So if you want to find out, okay, if you let us say, if you want to find out response due to any impulse that is non-unit, okay, so let us say response due to impulse I equal to, let us say, some other function p tau times d tau. Okay, so how do we do that? Or let me just don't use the integration sign here. Let me just say that it is a very small value. Okay, so that I can approximately say that the area is like p tau times d tau. It's like a rectangular area. Okay, so response due to this impulse, okay, we can find that as response due to unit impulse times the magnitude of this impulse. Okay, and this works for a linear system. So if the system is linear, we can employ this technique. Okay, because for a linear, I can directly multiply the response, okay, with the impulse magnitude to get the proportional response. Okay, so if I have a response, because remember when we said, okay, when we said that this is the variation, all right, when we said this is the variation of pt with respect to time, and we said that the variation looks like something like any random or like an arbitrary function. Okay, we have the function for unit impulse, but for these cases, these impulse small, if I divide it in small time duration, these impulses won't be unity. All right, so let us say this is at any time tau, okay, and this is the time d tau. Okay, and then like this is the 1 2 3 so on. Okay, so we want to find out for each of these strip like what is the response, so that I can directly find out by multiplying with this function. Okay, so multiplying h of t minus tau response due to unit impulse, okay, times the magnitude of the impulse. Okay, so this is the response at any time t. So let me, instead of just saying that, write it d of ut due to a small impulse. But this is just one strip here, right? This is just due to this at any time t. Let us say here I want to find out, okay, time t. So what do we do then? Well, as we have previously discussed, response at any time t would be the total response due to all the impulses, okay, up to the point or up to the time t. Okay, so if we integrate this function from this time 0 to t, okay, it would give me the total response at time t due to all the impulses. Okay, and let us see how does that look like graphically. So what I'm saying, let me say I'm drawing this graph here, okay, and then I'm drawing another graph here. Okay, so let us say in the first case, due to first impulse 1, it will undergo some free vibration. Okay, okay, for the second one, it will start little bit at time, okay, after d tau. Okay, and again it will give me some response, okay, which depends of course on the magnitude of that impulse. These two impulses are not same. Okay, it will again give me some response. Okay, and it will keep on doing that. Okay, let us say I draw at time d tau. Okay, so at this point also I will have some response. Okay, and if I keep adding them, okay, all the point till I get to this point, it will give me total response. So this is let us say du1, du2, and so on. This is basically du at any time t. Okay, or tau, let us call this du of, okay, we'll call this du of t. Okay, so the total response, as you can imagine, okay, initially it would be only due to this function, then it will keep on adding, and the response will keep on adding up or subtracting depending upon whether they are in phase or out of phase. Okay, so overall you will get some response, random response, okay, which might look like something like, I'm not trying accurately to like reflect that response function, but it would look like something like this, and this would be my total response. Okay, so as I said, I need to sum up response due to all the impulses. Okay, so the function that I have basically was this. Okay, it was p tau. Okay, and then I had h of t minus tau d tau. Okay, and I want to integrate this. If I want to find out, okay, the u at any time t, I want to integrate this dut up to time t equal to 0 to time t. So p of tau t, t minus tau d tau, and this goes from 0 to t. Now remember, here my variable is d tau. Okay, so the variable here is tau, not the time t. T is basically up to the point till which I want to integrate. Okay, so basically this impulse here that I had considered at any time tau, that is my integration variable. So if I vary this tau from 0 to t and sum up all the response to all the impulses, I will get the final impulse. So this expression here, okay, the expression that I have written here, it is called, okay, let me again rewrite it. This expression p of tau h t of t minus tau d tau, this is called convolution integral. Okay, it's called convolution integral, and it finds a lot of application in multidisciplinary field. Okay, you will see at many places this convolution integral. Now for our case, okay, for single degree of freedom system, okay, we already have the expressions h of t minus tau for damped and undamped system. So we can substitute it here and we can get the expression for the ut due to any arbitrary varying force pt. Okay, so that expression can be used to obtain the response, and that expression, let me just write it here, ut, let us first write for a damped system. Okay, I can write this as m omega t 0 to t. Remember, integration variable is tau. Okay, I have this exponential term which is t minus tau. Okay, and there is p tau term here as well. Okay, so let me just do this. Let me first write here the p tau e to the power minus zeta omega n t minus tau, and this is sine omega d t minus tau d tau, and I integrated from 0 to 2 to get the expression for all the analytical expression for this ut. Okay, remember, I'm able to do that. I'm able to simply sum up all the function because I'm assuming that all these functions are linear. So my structure is linear. What basically linear means, let us say if my structure is linear elastic, okay, so the fs versus u is basically like this. Okay, so the response I can directly sum up from the individual responses. Okay, so this convolution integral are strictly for linear systems. Okay, because we are using method of superposition. Okay, we are using method of superposition. Okay, so we have obtained this expression for damped system. Okay, and if you put the value of zeta equal to 0, Okay, you can get the expression for undamped system as well. Okay, which is not very difficult. Again, we'll write it as p tau e to the power minus zeta omega n. Well, there won't be any zeta term here. What I'll just simply get sine omega n. Okay, t minus tau d tau. So this is for undamped system. Okay. Now, one thing to note here would be in all these scenarios, we had considered U0 or initially that system was at rest. So at rest initial condition. Okay, so when we said that my force is actually starting, I just considered the effect of force, assuming that the system was at rest. But how about my system was already had some initial condition, like it had some initial displacement from the position of equilibrium and it had some initial velocity. Okay, if those values are non-zero, okay, so we had obtained the solution for at rest initial condition. For non-zero, okay, for non-zero initial condition, okay, you need to find out the response due to initial condition, like it's a free vibration. Okay, you need to add the response that you get due to free vibration with initial condition of u0 and u dot 0. Okay, which is not very difficult. We already have derived the expression for this for undamped free vibration and damped free vibration. Okay, so that needed to be, if it's like, you know, had any kind of initial condition, that needed to add up to this expression that we have derived here. Okay, this is specialized form of convolution integral that we use for our case is called Duhamel integral. Okay, this is called, just giving you some terminologies here so that when you see that you remember, this is called Duhamel's integral. Okay, and it is just in a special, like, you know, case of convolution integral. Okay, now as you can imagine, basically what we are trying to do here, okay, for any arbitrary excitation which are not periodic or harmonic, okay, so we had obtained for periodic and harmonic loading, okay, the analytical expression for u of t, but it is not so simple for any arbitrary varying function. Okay, so p tau, if it's a very simple function, then I can integrate this expression, okay, and obtain the solution for ut. Okay, but if p tau is very complicated, okay, if it's very complicated, then perhaps I won't be able to evaluate the integration, okay, analytically, and then I'll have to go into numerical integration. We will which we will see in a like, you know, future chapter. Okay, but instead of doing that, there are better methods to calculate the response for the numerical response instead of just integrating the Duhamel integral. Okay, so this was just to give you an idea that if there's any arbitrary non-periodic or non-harmonic function loading x function pt, then how to get the response. Okay, it might not always be the, like, you know, best method to go about finding the solution of a response of a single degree of freedom system, but it's like, you know, it's good to have a knowledge of this function. Okay, all right, once you understand the Duhamel integral, let us now go into some special cases of non-periodic loading. Okay, and then we are going to see the calculate the response. Okay, so what I would like to start with is step force. Okay, a step force is typically defined as a force, okay, that you apply suddenly. Okay, so it is like a step and then you maintain over time. Okay, so let us say a load of amplitude p naught, okay, is applied suddenly and then it is maintained over time. Now in very first chapter we had already find the solution to this using the conventional by solving the differential equation. Okay, so basically if you consider an undamped system, we can go ahead and we can find out the solution to this using homogeneous complementary solution plus the particular solution. And we had seen that for an undamped system, we had obtained the ut was coming out to be p naught by k times 1 minus cos omega nt. Okay, this we had obtained using solving the differential equation. Okay, the same solution can also be obtained, okay, just to demonstrate you, okay, the application of Duhamel integral. Let us find this same solution using the Duhamel integral. Okay, so remember, for an undamped system, Duhamel integral say the response is basically 0 to t, okay, p tau sine omega n t minus d tau. This is the expression. Now the force is actually constant, okay, so it doesn't matter what time you consider, p tau would always be equal to p naught. All right, so if you substitute it here and integrate this expression, okay, let's say this is p naught sine omega n t minus t tau. Remember, we are integrating with respect to integration variable tau. Okay, so this we can write it as, let us take p naught outside, this would be minus cos omega n, and then minus minus would get plus, so this would be basically t minus tau omega n 0 to t. And after you substitute the value, and remember, if I take omega n outside, m omega n square would be k, so this would be equal to p naught by k. If you substitute the these limits of the integration, I will get this as again 1 minus cos omega nt. Okay, so I mean, in this case you just happen to find out that this might be easier to do like that. However, for as the p tau or the loading function gets complicated, Duhamel integral tend to not be a good method to calculate the response. Okay, so in this case, what do you see? Response to a step function, okay, p naught by k. Okay, we say that if this is the response like this, okay, p naught by k is nothing but the peak value of the static displacement. Okay, so my dynamic displacement history is represented like this. So this is nothing but basically equilibrium actually shifts from 0. Okay, if I try to plot the response from 0, it oscillates about ust naught, which is basically p naught by k. Okay, so let us say initially it was here. Okay, as you apply this sudden load, start oscillating about this load or this static displacement. Okay, this is how the response would look like. Okay, so basically when you apply a step force, okay, what do you see? The system start oscillating about its natural basically frequency, okay, about a new equilibrium position, which is the static displacement of the system, okay, due to the load p naught. All right, once you know that, let us see what is the maximum value of this ut, or basically the peak dynamic displacement. Now in this case, as you can see, this function is actually varying between cos omega nt between +1 and -1. Okay, so the maximum value would be when cos omega n is -1, or this I can say the maximum would be 2 times ust naught. Okay, that would occur when cos omega nt equal to -1. So as we have seen, if you had a statically applied load p naught, okay, what would be the deformation? P naught by k, and that is what you have been studying till now before this dynamic course. Okay, however, if you apply this as a step force, okay, you get a dynamic displacement which is twice the static displacement. So it depends how the load is actually being applied. Okay, so if the load is applied suddenly like a step force, then you get a displacement which is almost 2 times the static displacement. Okay, and so this is for a undamped system. We can follow the same procedure for a damped system as well. Okay, so for a damped system as well, the response to the step force can be calculated using the same expression. You can use the Duhamel if you like, but you will see that Duhamel integral becomes very complicated in this case. Okay, and you can go ahead and perform that integration and have a look at it. The integrand that you will have here is basically, okay, 0 to t. Remember, p of tau would be p naught here. Okay, so I'm just writing p naught times e to the power minus zeta and t minus tau, and then I have the second term here. Okay, and if you go about integrating this function, it gets a little bit tricky, you know. While you can still find it, okay, not okay. Okay, you will see that it might not be the best possible way to go about it. So let me just write down the final solution for this. Okay, you get this as expression for the response of a damped system, okay, to step force. Okay, all right, so this is what do you get. Okay, and if you see again, this is oscillating about this UST. However, the amplitude of the second term, okay, so this is now oscillates with the frequency omega d or time period td. Okay, but with time, because of this exponential term, it starts to decrease. So the amplitude starts to decrease. So let us say this was the undamped system. Let us say this was the undamped system. Okay, damped system, what will happen depending upon the value of damping, the response will start to decrease and go like this. And if the damping is very high, okay, it will go to this one very quickly. Okay, this is u of t here, and this is time t. Okay, so this is what happens. Now in this case, you saw that utility of Duhamel integral, it won't be that effective. I mean, in this case, if you had this expression, let us say, to solve for a damped system, okay, if this is equal to p naught, you might be just like, it might just be easier to, like, you know, find it using the common method of basically the solution of a differential equation. Okay, so if you remember, particular solution, we write it as p naught by k here, and complementary solution we write it as e to the power minus zeta omega nt a cos omega dt plus b sin omega dt. Okay, so the total solution you can write it as p naught by k times e to the power minus zeta omega nt times a cos omega dt plus b sin omega dt, and you can substitute the initial conditions which we have assumed at rest initial conditions. If you substitute this, you can get the values of this constant a and b, and you will get the same expression. Okay, and as I said, the response looks like, so this is undamped, damping is equal to 0, and these are the curves for, let us say, some intermediate value of damping, zeta 1 or zeta 2. Okay, so this is what the response to a step function looks like. Okay, and let us say if your goal, okay, is to apply a step force, okay, so that you minimize the vibration. Okay, one of the example would be like, you know, you take a, let us say you take a weight, okay, and you put it basically, put it on any scale, okay, to measure this weight. Now you don't want too much of vibration because the reading would be fluctuating, keep on fluctuating, and if the damping is very small, it would keep on fluctuating Okay, and it won't give you correct reading. So let us say if you want to weigh it, in weighing machine what happens? Okay, the way it is designed, it is in a spring. Okay, and this is like a step force, right? What is this step force? This is like mg acting suddenly here. Okay, so in this case you assign very high damping. Okay, so that as soon as you drop this weight on the top of this digital weighing machine, okay, it comes to rest very suddenly without any vibration to whatever the value mg that is being applied. Okay, so it will converge to the value of mg. Okay, all right, so this was the response to a step force. Now we will delve into a different kind of force, which is called basically ramp or linear, basically ramp force. Okay, so let us now consider ramp loading. Okay, now when we said that, and that in this case, remember we said that if you apply this load statically, okay, and if you apply this load as a step function, the step function, suddenly applied step function gives you displacement which is twice the statically applied displacement. Okay, now what do you mean when you say that you would apply it statically? Okay, one way to define is basically you apply the load so slowly that it does not produce a lot of dynamic effect. Okay, and to do that we basically apply ramp loading. So basically a ramp loading looks like something like this. Okay, so if this is the variation of pt versus t, okay, it linearly increases up to the value of load that you want to apply. Let us say this is p naught. If you want to apply p naught, now you are not applying it suddenly. Now remember, in the previous case you applied suddenly. Now you're not applying suddenly, you are applying, okay, slowly, or I won't call it slowly, it depends on the rise time. Let us say this is defined as the rise time. Okay, rise time is basically time taken to reach the amplitude of the force in a ramp loading. That is, we call it rise time. Okay, so in this case basically we are applying something like this, and depending upon the value of tr, we will see later that our solution differs. Okay, if tr is very small, then it is almost like a step force. Okay, if tr is very large, then it is like, you know, constantly linearly increasing function. Okay, now for this let us first find out response to response to linearly increasing force. So what I want to find out, when the loading is still in this zone right here, okay, how does the response look like? Okay, so if I apply, so we will call this when it is still in the within still the linearly increasing force. Okay, linearly increasing force. Remember, for this case the pt I can write it as p naught t by tr, okay, for t less than tr, and it is equal to p naught for t greater than tr. Okay, let us put a equal sign here. Okay, so we want to find out when it is still in this range, what is the response? Okay, and that is not very difficult to do. If I consider a undamped system, this is the equation that I get for my equation of motion. Okay, this is the differential equation that we get. All right, and we can go ahead and find the solution to this. Again, you can utilize Duhamel integral. It won't be that difficult in this case. Okay, or you can go using the conventional method. Now in this case, let us go with the conventional method. We know that particular solution I can use as, okay, p naught by k t by tr. If we take this as a particular solution, then this is one of the solutions that satisfy this equation. And complementary solution, you know that it takes the form of, for an undamped system, okay, we can write this as a cos omega nt plus p sin omega nt. So my total solution becomes a cos omega nt plus p sin omega nt plus p naught by k t by tr. And if you substitute the at rest initial condition u0 equal to 0 and u dot equal to 0, what you will see, ut Okay, you can get the value of or the expression for ut as p naught pi k t by tr minus sine omega nt by omega n tr. Okay, now if you look at, let us just consider the linear part of the force here and then try to plot it. Okay, this is my t. The first part is nothing, okay, but the particular solution from here. Okay, it is the particular solution from here, and this is basically a linearly increasing function. Okay, so the first part is basically p naught t by tr multiplied with a factor of 1 by k. Okay, and this is basically ust. Okay, remember what did we call when we say time variation of ust is when you consider a zero effect of mass in the system. Okay, so you substitute mass equal to 0 and whatever the force, basically you get pt divided by k. Okay, that is basically your ust, and that is what is it is here. Okay, so remember pt was p naught t by tr. Okay, so this is p naught t by tr. Okay, so this is the force pt that is being applied. Okay, and instead of force, let me just write here the response u of t. Okay, this line is my ust t, and because if I'm still considering in the linearly increasing zone, it has still not reached the peak. Okay, so there is nothing like it is still increasing. There is no peak value of ust yet. Okay, and this is basically an oscillating function sine omega t. Okay, when we sum this up, these two functions, okay, remember this function, the second part is looks like something like this. Okay, and depending upon value of omega n and tr, okay, its amplitude would differ. So the total response when you sum this kind of function and this kind of function, okay, it would look like something like this. Okay, so basically the system start to oscillate again at its natural frequency omega n. Okay, however about its static solution. Okay, if there was no mass in the system, no dynamic effect. Okay, this is my u static and this is my total solution. Okay, the difference is basically your this solution here. So this is my u of t. All right. Okay, so we have seen that for the linearly increasing part, this is how the response looks like, and depending upon the value of omega n and tr, it might look like something like this, or it might also look like something like this. And in many cases, this is not actually desirable because I want to take the system statically without creating much vibration, and if I get something like this curve here, then it is not desirable. So for those kind of system, okay, we have to apply or we have to increase the value of tr. Okay, increase the value of tr so that this actually reduces. So when you increase the value of tr, it becomes closer and closer to the static solution. Okay, all right, we are going to conclude here. In the next class we will see, okay, to this ramp loading, after we consider this phase as well, how do we get the total response, and we'll do that for damped system as well as undamped system. Okay, all right, thank you.